Hello, this is my Physics 2211 Lab 2 Motion of a Falling Object. The purpose of this lab is to observe the motion of an object from like a projectile. I will be constructing two computational models, one that includes only the effect of gravity and one with effects of gravity and air resistance. Finally, I will compare the models to my observations by plotting their trajectories in the same graph. The physics principles I will be using include Newton's second law, which states that the net force is the rate of change of momentum over time. So when a net force is zero, the velocity is constant. This concept leads to the velocity update formula. I will also be using the concept of weight, which is a force equal to a mass times the acceleration due to gravity that always points downward. I will also work with the drag force, which is a force opposite to an object's motion represented by the formula of the negative of the drag force constant times the speed squared times the unit vector of the velocity. Finally, I will be using the position update formula. As a previous result, I have found that a model that considers that drag force is the most accurate representation of the trajectory of the object, since when the velocity is not zero, the drag force of an object is significant. There is a screenshot of the video of my object in Tracker, which I used to determine its position. It's important to mention how the system in this experiment is the falling object, while the surroundings are everything else. The conditions of my experiment include how the initial time was 0 seconds, and how the time after one frame, or delta t, is 0.033 seconds. The initial position is 0.019, 0473, 0 meters, and the position of the one frame is 0.052, 0505, 0 meters. So the change in position after one frame is 0.033, 0.032, 0 meters. With this information, we can determine that the initial velocity is 1, 0.969, 0 meters per second. Regarding my computational model, I have included the conditions such as initial time, delta t, the initial position, and velocity, and included the update velocity and position formula. I have also included the object's mass, which was 0.005 kilograms, and acceleration due to gravity, which is 9.8 meters per second. It was used to determine the object's weight. For the gravity-only model, I made the drag force constant 0, while for the drag force model, I made it 0.014. This is the iteration loop of my computational model. While the time is less than 0.367 seconds, which is the length of my video, the net force will be the sum of the weight and the drag force, and I will upload the object's velocity and position after each delta t, which in turn will update the net force, and so on. This is the trajectory comparison graph. The blue dots represent the observed positions, the red dots reflect the computational model without the drag force, and the yellow dots reflect the model with the drag force. The results reflect how initially the positions of the three models are approximately equal, since when the velocity is close to zero, the drag force will also be close to zero. However, as the horizontal position increased, the vertical position of the gravity-only model deviated from the other two. This is because since the velocity is now not zero, the drag force is significant. This explains why the gravity-only model descends faster and why the drag force model is the more accurate representation of the trajectory of the object, as they are similar to one another. Some possible sources of error are how one I consider the x and y axis and not the z axis, possible inaccuracies when using Tracker, and that the drag force constant may not be accurate. The first additional question is if there is a terminal velocity. In the drag force model, there is a terminal velocity in the y-axis of negative 2.3 meters per second. This can be seen as the velocity changes less and less as it approaches this value. Because the velocity becomes approximately constant, the net force in the y-axis is 0. So a sum of the drag force plus the weight is 0. The gravity-only model doesn't have a terminal velocity, which could change if it considers the drag force that opposes its weight. The second additional question is if the object was thrown straight up with the same initial speed, how would the time it takes to reach the ground change? After using a new computational model, we can see that it takes less time to reach the ground. The object is still 0.183 meters high when the original case had already hit the ground. This could be because the drag force affects the parabolic motion more because of its angle motion. As a conclusion, the drag force model is the more accurate representation of the trajectory of the object. This is because the drag force affects an object's trajectory, as it opposes its motion, leading to an early descent and its lower maximum height. This is reflected in a graph as it has a lower vertical position compared to the other two models, which are considerably similar to one another. Thank you.